Ping, for the introduction, and I would also like to thank everybody for being here today. It's an honor to speak at your institute, especially for being a foreigner. So I hope you will be able to follow my presentation. I'll try to be as clear as I can. Of course, if you have any questions or don't understand something that I've said, please let me know. In the next hour and a half, what I would like to do is give you an overview of the subject of light pollution, with some application to Taiwan in particular. And I hope that by the end you'll have a feel for why we think this is an important subject and what we can do here in Taiwan to try to improve the situation to preserve dark night skies. So here's an outline of the subjects that I will cover. First, I'm going to give you a very general background about this subject. I will give you then a little bit more detail about how it applies to astronomy and what our concerns are for astronomy moving forward in an era when light pollution is growing very rapidly around the world. I'll tell you about some strategies that we have used in my organization in order to try to raise awareness of the issue of light pollution, and then to do something about it, to create change that results in a darker night sky while preserving the needs for light at night on the ground we have as humans. Because of course we still need to get around in our world at night. We need to do so safely, and we think that there is a way for those issues to coexist. From there, I'll tell you about some of the best policies that we know about, both legislative policies and regulatory, as well as best practice that comes from our work with the outdoor lighting industry. And then I will conclude with some speculation about the future of this subject, both worldwide as well as here in Taiwan. So I would like to begin by giving you a bit of an overview of the subject of light pollution. So to start, this is a term that's not necessarily familiar to people, but it is one that is increasingly understood within the context of environmentalism around the world. And people who work in the conservation profession see it as something that's important as the pollution of our air or water, for example. There's no official definition of light pollution. There are different ways of thinking of the problem. The version that I like is this sentence that puts an emphasis on the problems that are associated with using all of that light at night. So it distinguishes useful light from the variety that's not useful, and therefore creates a condition similar to other forms of environmental pollution. So this is my working definition, that if there's some kind of adverse or unwanted effect of the use of artificial light at night, then we would broadly call that light pollution. Some people, when they hear this term, they think of this over here. So of course, you know, over here on the left, there's a lot of stars in the background. It's very dark on this side of the picture. Here's a city in the foreground. You don't see as many stars in the night sky above that. That's a phenomenon that we call sky glow. And I will come back to that subject because it's very important for astronomy. But all the other aspects of lighting at night, which could include glare, could include what we call light trespass, where light moves from one property to another and is unwanted. The tendency to use too much light in our cities, these are all manifestations of light pollution. So it's a very general term. And I've now, on a couple of occasions, used this term artificial light at night. So you will hear me refer to ALAN, A-L-A-N. So what that means, it's an acronym that stands for artificial light at night. And in these pictures, I've put it into two different contexts. There's a distinctly outdoor version of ALAN, and there's an indoor version. And mostly what I will be talking about is the outdoor version, because this is where we have an environmental impact. It has an impact to astronomy, public safety, etc. You might see some media reports about artificial light being detrimental to human health, which is a subject that's fairly new in biology right now, but it's very concerning because the more information that we learn about it, the more that we find that exposure to light at nighttime when the sun is down, and particularly of certain colors, as suggested by that blue light coming from the computer monitor, may be hazardous to our health as humans. Mostly I will not be spending time on that because that's a subject for indoor circumstances, because The majority of our light exposure as humans at night is indoors. So I'm noting that it exists, but letting you know that it will not be a focus for this presentation. So anytime you hear me use the term ALAN or ALAN, what I'm referring to is artificial light at night. So what can I tell you about ALAN? Why is it something that is of concern to us? Well, for one thing, I would say in a broad sense that ALAN, artificial light at night, is unnatural. And the term artificial in English is suggestive of that. It's something that's caused by humans, and it is of a nature that we do not experience outdoors away from where humans are. And so to illustrate this, what I've shown here are some spectra of different kinds of light sources, starting with a very natural source of light, which is the sun up here at the top. This is just in the optical part of the spectrum. And I'm stepping down through the other items on this list that are other artificial sources of light. And they are going from sources that are more or less like the sun to increasingly not like the sun, and that's what's important. So the sun is emitting a thermal spectrum. It's essentially a black body with an effective temperature of around 6,000 degrees Kelvin. And this continuous spectrum is broken by some absorption lines, but otherwise most of the colors being emitted by the sun make it to the top of the Earth's atmosphere. They're transmitted through the atmosphere. Some of the light is absorbed. And so what we get at the surface of the Earth is somewhat modified by the transit through the atmosphere, but it looks very much like a black body spectrum. But as you'll notice, as we step through these other sources of light, there are areas where light is either missing or light is more or less prominent, especially in cases of high-intensity discharge lamps that use a vapor of atoms to produce light where you have very bright line sources. And the reason that this is important is because our biology on Earth evolved with the expectation that the dominant source of light in our environment is sunlight. And then after the sun goes down at night, there's light from the moon, stars, planets, but those are very small in comparison to the intensity of the sun. So when we talk about taking a spectrum, for example, like light-emitting diodes, which I'll be talking about a lot in this presentation, the spectrum of those light sources is very different from a thermal spectrum. And as a result, there are certain biological impacts of that light that are different than sunlight. Similarly, there is a concern that I'll tell you about regarding LED light and impacts to night sky, especially that affect our ability to do astronomy from the ground. So keep in mind that all of these sources, with very few exceptions, certain kinds of radiant light sources like halogen lights have a more or less thermal spectrum, but the majority of ALAN sources do not. They have non-thermal spectrum, and that has consequences of its own. So as a result, ALAN is what I would say is biologically active. That means that it disproportionately affects some biological systems rather than others. And to illustrate this, I have a few spectra superimposed on the same plot here. And again, there's a focus on white LED light because that light is becoming so prominent in our outdoor landscape. So there's a lot of exposure of this kind of light, not only to humans, but other kinds of living things as well. So in this picture, the heavy solid line here is the spectrum of typical white LED that generates white light through a fluorescent process. So underneath every white LED is a blue LED. So we start with high energy light, we shine it off of a material that's called a phosphor. And the phosphor has a chemistry to it. Depending on the details of the chemistry, we can convert the white or the blue light that's in this large spike here at about 470 nanometers into green and yellow and red and the other colors so that the combination of those appears white to the eye. But underneath there's a blue LED. The reason that that's important is that some of that blue light makes it through the phosphor and is directly emitted into the environment. This thinner solid line here is what we call the photopic response curve of the human eye. So under ordinary bright lighting conditions, such as in this auditorium, or if we went outside under the daytime sky, the sensitivity of the human eye to light has a very distinct peak around 550 nanometers. That means our eyes are most effective at rendering images to our brains if we see light with that wavelength. And of course, it falls off on either side. So under bright lighting conditions, our eyes do not do well down in the violet and blue part of the spectrum, and they don't do especially well in the far red part of the spectrum. So now you can imagine if we're lighting the world at night with this source, this solid heavy line here, much of the power in this blue spike falls outside of the photopic response curve. So we tend to call those junk lumens in English. And what we mean by that is it's light that's being emitted, but that the human eye is not very good at sensing at night. So therefore, we're putting light into our environment that doesn't even help our ability to be able to see safely and move about at night. So it's a literal waste of light and a waste of energy if we emit a lot of light with those colors. The other complication is this dashed line right here, which shows what we call the action spectrum of a hormone in the human body called melatonin, which you might have heard of. Melatonin is involved in the circadian regulation of our bodies. So we are entrained to a 24-hour cycle that's defined by the rising and setting of the sun and the varying length of the day throughout the seasons. Melatonin is something that helps us stay in line with the setting and rising of the sun so that the length of the day does not affect us too much throughout the year. So what the dashed line represents is the sensitivity of our eyes to light that either causes the creation or promotes the destruction of melatonin in the brain. So at night, when the sky is normally dark and under ordinary conditions without cities, we would be in a dark environment, there's a lot of melatonin production just before we go to sleep at night. And it appears to have something to do with the mechanism by which we fall asleep and stay asleep for a certain number of hours. So you can see the problem here is that while that cycle is very dependent on light at that blue wavelength of about 470 nanometers, we're now putting light into the system at that time when the brain and the body do not expect it. And therefore the result is not only an inability to sleep properly, but the possibility that we are setting ourselves up for health effects later on. Melatonin is a signaling hormone in the body, and it's telling the body to do certain things at certain times. But if melatonin is active at inappropriate times, then it may cause the body to create different processes that shouldn't be happening at night. They're supposed to happen during the day. There's a link to obesity in humans. There's a link to type 2 diabetes, and also to certain forms of cancer. So right now we cannot yet say that this light is causing cancer in humans, but it may be a contributing factor in some cases when people do later develop cancer. So ALAN is biologically active, and it's important to keep that in mind. As a result, ALAN is often harmful for a variety of reasons, not just for health, but also to wildlife that experience some of the same biological rhythms that we do as humans. Of course, it doesn't end there. Some of that light will end up in the night sky. Some of it has to do with energy use, which ties into energy security and climate change. And then, of course, public safety, because we want safe streets at night. We want people to feel safe driving and walking and riding their bicycles. But we want to do so in a way that doesn't create more of a problem with safety than we solve. So ALAN touches on all of these subjects in one way or another. And there are a couple of specific examples to point out with this. So for the ecology, this image shows a picture of hundreds of dead birds. These birds were collected on one night in the Canadian city of Toronto. And these are all birds that died of collisions with the windows of buildings that were lit. So light was coming out from the building through its windows. This is very confusing to birds, especially along routes where birds migrate. So the light is very attractive to them. It draws them into cities. They begin flying around the buildings, and eventually either they will drop because they become exhausted, or they will fly into the windows. This is just one night in one Canadian city. The estimates vary between somewhere around 10 million to as many as 1 billion birds per year die in this manner. And some of these species are very sensitive or even endangered. So this is one example where there's a very particular kind of harm to an animal species that's caused by exposure to this artificial light at night. I also mentioned energy security and climate change. And we know that the problem associated with carbon emission and the warming of the Earth's climate is rapidly approaching a tipping point, where we will probably no longer be able to recover from the damage that has been inflicted on the environment and to our climate. And so it's more important than ever to reduce our energy consumption as much as we can. One way that we can do that is by addressing outdoor lighting, which takes up something like 15 to 20% of all of the world's energy generating capacity. So to the extent that a lot of that electricity comes from the burning of fossil fuels, for the countries that haven't converted over to more renewable forms of energy, there is a direct link between artificial light at night and the emission of carbon that is contributing to climate change. One way out of that potentially is through very energy efficient lighting such as LED. And when it is deployed carefully and thoughtfully, LED can be a very good solution to this problem that can help us deal with the problem of climate change. But as I'll show you in a moment, there's a possibility that we also go too far in the other direction, and that LED is contributing to this problem more than it is helping to solve it. And we now have some evidence that actually supports that possibility. So keep in mind that Alan is an important influence in climate change. As I mentioned, there are known and suspected risks to human health that result from nighttime light exposure. Again, much of that light is coming from our indoor spaces, but some of it is also from the outside. The brain and the body do not know the difference between a photon of light emitted in an indoor space and one that's emitted in an outdoor space. So all of that light contributes. These are statements from the American Medical Association, mostly involving shift work, but also World Health Organization, suggesting that this chronic nighttime exposure to light is probably involved in some of the processes that eventually lead to certain kinds of chronic human diseases. So limiting light exposure as much as possible seems to be something that is good for promoting good health. But this problem is not one that's limited merely to the West, even though it's very dominant in the part of the world that I come from. Truly, Alan is a global phenomenon now. This map represents our best understanding of the problem to date. This was published in 2016 and is the result of a campaign to observe the Earth with orbital satellites during the period of 2012 to 2016. And in that time, satellites orbiting the Earth are seeing the Earth at night. They observe the Earth during the daytime, mostly for meteorological studies, but then at night they see the light from our cities. What this map shows in the false colors is the amount by which the brightness of the night sky, as seen from the ground, is higher than a background that is established by natural processes in the Earth's atmosphere. So if we say that a natural night sky with no light pollution, if we call that 0, you can see that much of the world is still in these areas where there is no influence from artificial light. But of course, in the more industrial and developed countries, you see increasingly warm colors on this scale. So it's going through the blues, the greens, red, and eventually to white. There are some cities in the world where the background level of light in the city is up to 1,000 times higher than the natural background. And so this has a very important effect on both these cities and places that are much further away, because you'll know that in some parts of the world, such as in Europe and in the eastern half of the United States, there is no more natural darkness. It is now all gone throughout those parts of the world. And we can't merely assume that in other places, such as the Amazon basin of South America or the Sahara Desert, that we can assume those places will stay dark with time. There's a lot of development, for example, in production of oil and gas that takes places in areas that are far from where the populated cities are. So the potential for this light to come into these very remote, very sensitive areas throughout the world is high. And the important takeaway from this slide is that the problem that I'm discussing is not merely one of the developed economies of the world, it's a problem for every country. So if I zoom in on the part of the world that we're in, here is a map of Taiwan. And as you might imagine, the light generally follows where the people live. So there's a lot of light on the west coast. There are a few cities on the east that have population centers where there's light, but you'll notice that there's this large interior in the mountainous region in the center of the country where the color is more blue, which indicates less light. So this is important. We have a very strong delineation here between the populated coastal areas and the interior that remains naturally dark, largely because of the landforms themselves. The mountains are what prevents a lot of development in those areas. So when we start to think about strategies that would work to help deal with this problem in Taiwan, we have to know something about the geography of the island and where the centers of light are already. But you'll notice that even the darkest parts of the country right here in this blue region still are not quite at the point that they represent a natural level of darkness. And what that's telling us is that the light from the cities on the coasts scatters to very large distances away from them. So if you look at the Taiwan Strait between Taiwan and mainland China, that there's no area here that becomes this darker black color. So between the light on the mainland and the light on the west coast, the entire Taiwan Strait is lit at night. The light coming from the two countries. That has important ecological consequences. And if we want to address those, we need to talk about the light that's in our cities. So I've shown you where the light is in the world, which inevitably leads to a question of how much is it changing? And this is one of the more technical slides in my presentation, so I'll explain what you're looking at. So this is from a study that was published about 1 year ago by Kaiba and coworkers in Germany. And what they did was they looked at all of that satellite data of the night lights on Earth, and they broke down that distribution of light by country. So you can see the countries of the world pretty distinctly in this map. On the left, this shows the rate of change during a 5-year period in terms of the land area where there was indication of light. In order to determine what that number is, they had to account for what are called stable lights. So those are the lights of cities and villages that are always on every night. So they attempted to exclude light from sources such as wildfires, lightning associated with thunderstorms, and other forms of natural light. So it does not include those sources. We're looking at the stable lights on the ground that we know are associated with where humans live. And there's a rate of change that is from very slightly negative to slightly positive. This yellow color in the middle means no change during the study period. So you'll notice that many countries in the world are very positive. They're on the red end of this scale. So that means that the area of land that is lit at night has been growing, in some cases up to 10 to 12% per year. The figure on the right shows, instead of the land area that is lit, it shows the quantity of light. So summing up all of the light that's being emitted by that country and asking, does that change over time? And we see a similar pattern. Most of the colors in this world map indicate that lights are getting brighter. Interestingly enough, note that the United States, North America, and Western Europe are not where lighting is changing very quickly right now. It's the developing world. It's places like India, it's sub-Saharan Africa. Because as I pointed out in this picture here, many people live in this part of the world, right? This is not just an indicator of where the population centers are. There's a large population in sub-Saharan Africa, but they are not yet at the development stage that the West is. So right now, some of those countries are very rapidly consuming new light. What I find interesting about this map is that you'll notice that some countries are blue. And in particular, you'll notice that Syria and Yemen are blue. Those are indications of civil war, destroying the infrastructure in those countries, reducing the overall amount of light that those countries are emitting. So what this is telling us not only is that artificial light use is growing very rapidly throughout the world, but it's telling us something about ourselves as humans and how we're using the land in some cases, and in some instances it's to a destructive effect. So there's a lot that we can learn just by looking at pictures like this about how humans are using light.
John, what's happening in Australia?
Australia, that's a good point right here. This is one case where they were not able to completely remove the natural influence of light. And there was a time here when there was, just before the study period, where there were a lot of bushfires in Australia. And then during the study period, there were fewer, so it was an apparent decrease. So that's not an indicator of human activity, and it's one of the only countries that's true. Overall, if you look at all the countries in the world, both the area and the radiance are changing on a global average of about 2% per year positive all around the world. But individual countries are as high as 12 to 13% per year. A lot of this effect is attributable to the introduction of light-emitting diodes. This is a technology that, as I mentioned, is a very efficient way of generating light. It requires very little electricity in order to produce a lot of light. The consequence of that is we might tend to overuse it. The nature of the change is one that is visible from space. This is the city of Milan in northern Italy. And there's a picture that's taken from the window of the International Space Station in 2012. So these are astronaut photographs. When the astronauts have free time, they like to take cameras and point out the window. And at night, they see the light from our cities. So in 2012, you can see the majority of this light is orange. This is a true color image. That orange light is produced by sodium vapor lamps. So they used an electrically excited gas of sodium atoms that emit light at certain wavelengths, but it's dominated by the D transition at about 588 nanometers. So between 2012 and 2015, when the second image was taken, the core of the city of Milan was changed from the sodium lights to white LED lights. So the color of the city literally changed as seen at night as a result of making this transition over from the old technology of sodium vapor to the new technology of white light-emitting diodes. So it's something that is literally changing the appearance of our cities, but it also has impacts on the ground as well. It's not just the aesthetics of the cities as seen from space. So as I was alluding to, the consequence of this dependence on light-emitting diodes is that we might actually be creating a new problem, and that is something that economists refer to as a rebound effect. So what the graph here suggests is that when the cost of some kind of a product decreases, our tendency as humans is to use more of that product and not less. So think of the price of fuel. If you're driving a lot and the price of fuel goes up, you might think twice about doing so much driving. But if the price of fuel comes down, you don't scale down your driving as a result. People tend to buy more fuel. We're seeing a similar effect now with lighting, specifically with LED. And it has to do with the ready availability of this light, which has become very cheap to produce. So the concern is that all of the energy and electricity and cost savings that were promised by the world's transition to LED lighting, which was supposed to be good for the environment, might actually have the opposite effect. If the savings on electricity from LEDs is merely used to purchase and install more light. And so if you think about this concept and go back to this picture, if light is growing throughout the world, and we think that it's because of the rapid deployment of LED, and if there is a rebound effect occurring, then as this quotation that I've pulled here suggests, some of the claims about the environmental friendliness of LED lighting may be misplaced. Because instead of reducing our overall energy consumption, it's either unchanged or it may actually be increasing. And that wipes out the gains that were expected by moving to more energy efficient lighting. This is something that we should consider in the future as well, because there are technologies coming in another 20 to 30 years that will be even more energy efficient than LED. So know that we now have some evidence from the satellite measurements that this rebound effect is actually taking place. So what do we know about light pollution after studying it academically for about 40 years? Well, I've shown you some images that suggest some of the summary points here, which are that much of the world is now affected by this problem. And it is not, again, merely restricted to the developed economies of the world. It's coming to all countries, that no one is really immune to this. And that a lot of people now live in a condition that's like twilight. So think of the sky after sunset, after 15 minutes, after 30 minutes, after 45 minutes. It's not yet completely dark. There's still some scattered sunlight in the sky. That intensity of sky brightness is now what many people living in cities like Taipei experience. It never becomes fully astronomically dark in our cities. And that feeds into the kind of problems that I was describing earlier, because we have this perpetual exposure to twilight. What don't we know about light pollution after studying it for 40 years? Well, there's a lot of things that we don't know. We're learning new things all the time about the biological effects, but we also want to know about its impact to the humanities. Is there value to tourism related to night skies? We think there is. We don't have a lot of data about that yet. What about the health effects? A lot of people want to know. If we pursue some of the ideas that I'm talking about today, will it be beneficial to our society or will it be detrimental to society? Is all of this concern about light at night misplaced, or is it very relevant to our condition now in the world? I think it's the latter, but we still have a lot that we still need to learn about this in order to be confident in the conclusions. So why is this happening? Where did we arrive here at after 130 years of electric light to where now our cities never become completely dark at night? We think that a lot of the problem traces back to a notion of a lack of awareness. That if people were aware of the consequences of the use of this light, both known and suspected, that they might think about it differently and they might use that light differently. So the task for those of us that are trying to change the world in this regard is to raise attention to this issue in the hopes that once enough people of the world decide that they want a solution to this problem, that their decision makers will listen and that we will be able to achieve this. And I think it's possible within the span of a human lifetime to solve this problem if we get to the point that enough people care about it. So what relevance does this have in particular to astronomy? Well, mainly it's this phenomenon that I mentioned earlier called sky glow. So in the picture that's shown here, there's a single source of light and it has a number of rays coming off and they're going in different directions. And I've numbered them according to some of the potential outcomes for where the light ray goes. But you'll notice that most of these make their way back to Earth. Some of the rays of light that are being emitted by a fixture will pass completely through the atmosphere, where they're possibly detected by Earth orbiting satellites, or they're seen by astronauts on the space station. Some of that light will be directed back down to the ground after a single scattering event. Light scatters off of small particles and molecules in the atmosphere. It's very wavelength dependent. So the Rayleigh scattering phenomenon that makes the sky appear to be blue during the day is at work at night. and some of the light is being more intensely scattered because it is of short wavelengths. Sometimes the light makes a reflection off the ground and then goes up into the night sky. Some of that light will make it through the atmosphere. Some of it will be scattered back down. But most importantly for astronomers are the scattering events that result in light entering our telescope apertures. And anybody who has had the experience of going to a darker area and looking back in the direction of the city understands why. So all the light that's scattering back down to the ground is decreasing the contrast between astronomical objects and the background sky. So in order to positively detect light from astronomical sources, we have to have good contrast with the sky background. If the sky level is very high because of sky glow, the chances that we will detect light from astronomical objects is very low. This is why, for one reason, that we tend to locate astronomical observatories far away from cities. We usually also put them in the mountains because the airflow over the mountains are better, so the quality of the images is higher. You'll notice that in almost all of these cases, the observatories are located very distantly from our urban centers in order to avoid this effect. LED is contributing to this problem and making it worse, and it is because of Rayleigh scattering. So what I'm showing you here is a simulation of the city of Flagstaff, Arizona. It's the part of the world I'm from. It's just one of our dark sky cities. This is a city where astronomy is very important. There are several major astronomical observatories located near Flagstaff, and they are an important contributor to the local economy. So since the 1970s, the city of Flagstaff has implemented lighting policy that is intended to reduce the effect of light pollution on those observatories. Right now, the street lighting in Flagstaff consists of what's called low pressure sodium light. So this is very orange light in its appearance. It's a narrow band emission of light around the sodium D line, which is very good for astronomers because it affects only a small part of the spectrum, and it can be filtered out. So you can put a filter in the beam of your telescope that effectively rejects the light from the street lights, and it means the contrast with the background is very high. So this top picture shows a simulation viewing Flagstaff from a distance of 20 kilometers with the current low pressure sodium street lighting system. So for the purposes of the simulation, transitioning from this scenario to this one, this is where we replace all of those street lights with white LED lights that have a correlated color temperature of 4,000 kelvins. So this is white LED light that is very rich in blue light, short wavelength light. But the number of lumens of light is the same in the two simulations. So we have not added any light here. We have just moved the light in the spectrum towards shorter wavelengths. But you'll notice that here the Milky Way is evident. There are quite a few stars. In the lower image, there are many fewer stars. The Milky Way is harder to see. Sky glow has increased. And again, we have added no new light. This is an equal distribution in each case in the quantity of light, but we have changed how the spectrum of those lights looks. So merely by transitioning from the old technology of sodium to the new technology of LED, potentially we would make the sky over the city of Flagstaff worse. I can tell you that Flagstaff will not do this. They've already committed to that. They want to convert their lighting system over to some form of LED, but they're looking at other alternatives that do not involve the amount of blue light emission in order to prevent this scenario from becoming true. But this shows you what might happen. And again, the reason is Rayleigh scattering. So the picture here is from Lugan, Gioboli, and Davis in 2014, and they did some numerical simulations with radiative transfer to demonstrate this effect. And what they have is related to the low pressure sodium lighting system in Flagstaff, the impact on the night sky is quantified with respect to that sodium light. And so as they go through these different colors, these different sources of light, so you have two varieties of sodium, you have LED at a particular color temperature, MH stands for metal halide, which is a very blue-rich source of light, and then finally a 5,100 Kelvin white LED. You notice that, relatively speaking, the impact at low distances is very large. In some cases, it's a factor of 6, 7, or 8 higher. But most importantly, even out at large distances, so now we're 300 kilometers from a city like Flagstaff, and the blue-rich white LED is still contributing more to sky glow. So there's a possibility here that moving over to this new technology is making the night sky brighter even at very large distances from cities. Because again, the probability that blue light will scatter on its trip through the atmosphere is higher than it is of other colors. So we have to be mindful of this during the transition from these old lighting systems to LED, that we don't inadvertently make the sky at large distances from cities considerably worse. So why does this matter for astronomy? Well, for one thing, telescopes are expensive. And if the solution you might think of is, we'll just put all of the telescopes in space. So if we can get above the atmosphere, we will never have to deal with light pollution again. That's fine, but here's the forthcoming James Webb Space Telescope, whose price tag is now $8.8 billion US and climbing, and may top out at $10 billion before it launches in 2021. But at the same time, at least in my country, the funding for astronomy and space science is essentially unchanged for the last 25 to 30 years. That's the lowest of these lines of the different subjects down here is physical science, and then just above that is astronomy and space science. So there's not more money coming into the world's budgets for astronomy hardware. So we can't assume that we can put it all in space and just deal with this problem that way. For one thing, there's a possibility that your telescope never makes it to orbit, or some other part of it fails during its lifetime. We saw that with the Hubble Space Telescope. If it hadn't been for the ability of astronauts to service the Space Telescope after launch, we would have lost all of the productive science of HST. So in the future, as these costs continue to rise, there will be more, I think, rather than less, pressure on ground-based astronomy facilities in order to make the science continue to be possible. However, bear in mind that the best locations in the world for doing astronomy on the ground are themselves not getting any darker. This is a view of one of the two Keck telescopes on Mauna Kea in Hawaii with light from the big island of Hawaii on the horizon. Right? This is one of the world's best sites for doing ground-based astronomy, and yet it's not the world's darkest sky. And that's a problem because there's already more than $1 billion worth of hardware investment at that facility. And building new telescopes there has become contentious. So if we have to go further and further away from cities in order to find places that we can do astronomy, these impacts are significant. And again, thinking back to the spectrum of these white LEDs and knowing what kinds of science are sensitive to short wavelengths in the optical, the possibility that we lose certain windows of the optical spectrum in order to be able to do astronomical observations is very high. That has consequences potentially for what kinds of science we might even think about doing in 20 to 30 years if we can no longer develop new and very expensive space-based hardware like the telescopes that will come after James Webb. So keeping this all in mind, the argument then becomes maybe it would be better if we tried to preserve the darkness that we still have here on the ground in order to be able to continue to do astronomy from the ground for a much longer period of time. So what can we do about this? What are the best strategies to try to address the problem of light pollution and sky glow in order to keep the night sky dark, but also to provide for the kind of conditions on the ground that are beneficial to animals and wildlife and humans, etc. Well, to answer that question, I would take one step backward and ask, why do we light outdoor spaces in the first place? Because this has something to say about the motivation for the lighting and why we're putting it in so many places and why the world is getting bright at the rate that it is. Fundamentally, it comes down to just a few things, right? A lot of the light that we use is reasonably so for public safety. It's our ability to find our way, whether that's on foot or on a bicycle or in an automobile, that we need enough light in order to be able to safely transit. So that's one reason. Certain kinds of light is targeted towards the performance of tasks. So in this example, there's a work crew that's working after dark. Excuse me. And they need to be able to see in order to do their work safely at night. So in principle, we're lighting just the site of the task that's being performed, and it should be ideally in the amount of light that's necessary to perform that task safely. But we also use light for aesthetic purposes. We can see this throughout a city like Taipei, that light at night is used to create a sense of ambience. It's to set a mood for a particular outdoor space at night. But you can also maybe go too far in the other direction and you create a very distracting display. So the challenge is how to accommodate all of these desired uses of light at night without creating a big problem as a result. Another reason that people often use light is because of a belief that outdoor spaces that are brightly lit are safer spaces at night. And by safer, I'm referring to the incidence of crime. At least in my part of the world, I think this belief is widespread, that people think that a space that is brightly lit at night is a safe space, it's a secure space, it's one in which they are not likely to become the victim of crime. It's hard to get across the idea that that thinking might be wrong. This is one of the best pairs of images that I can think of to illustrate what I mean by this. So here's a typical application that you might see in the United States, where the owner of an individual home has put a bright lighting fixture on the side of the house in order to light up this space next to it. There's a walkway right here. They might have some property stored in the little garden next to the house. But there's a fence surrounding the property and there's a gate that is open. And as the first picture shows in the upper left, with that very bright light on the wall streaming into the eyes of the observer, there's not a lot of contrast between foreground and background. And so you can tell there's a fence here, but not much more about it than that. But in the second picture, without changing any of the camera settings, the photographer simply reaches out his hand and uses it to block the light. And as a consequence, now you can see that there's a person standing in the open gate. So if the person in the open gate were a potential criminal perpetrator, and the person making the photograph was a potential victim, which of these two situations is more safe? Of course, I would argue that it's this one. Right? Keeping the light out of the observer's eye is very important, because a lot of light entering the eye has the tendency to cause the pupil of the eye to constrict. And it makes our depth of field very limited. And it again has a problem with the contrast there. So the point here is that merely shielding this light in order to keep the light on the ground where it's needed and not in the eyes of people who are passing by, that is more safe. The light in the scene itself is not what is creating the sense of security. It's the light that's properly placed that creates the sense of security. And that's what we want to promote. So adding light to spaces itself does not make them more safe, but it can actually have the opposite effect. This is another point that I find myself having to make very frequently in explaining why this subject is so important to us. Because of a belief that when we talk about dark sky, so that the night sky is visible, that it means turning lights off, which is not necessarily the best approach to the problem. We don't want a dark ground. We don't want to make the world an unsafe place at night where you have trouble seeing obstacles. We want a well-lit ground at night, which would necessarily result in less light in the night sky and a darker sky. So to be dark sky, so to speak, does not mean a dark ground that is dangerous. And I mentioned earlier as well the tendency towards more energy efficient lighting may be creating these other problems. A lot of lighting designers and a lot of municipal and even national governments have opted very strongly for very energy efficient lighting that uses as little electricity as possible, which again is a very good goal. But if the difference in energy efficiency is only on the order of a few percent, and the difference in that is either a very well-designed, very safe lighting installation or one that's highly inefficient and may not be safe, I would argue that we should sacrifice a few percent of efficiency in order to get a better outcome for the people who will use the light. So we shouldn't sacrifice some positive benefit of the light simply because it costs 1 or 2% more in terms of energy use. It's something that's a difficult sell sometimes to local governments. It's a difficult sell to business owners who are concerned about the cost of providing this. How do we get them to go along with this? That's the rest of the talk, essentially, is how do we go from this into action? But we have to keep in mind that the efficiency of lighting is not the only consideration in our designs. The idea is that if we combine mindfulness for the use of light with the technology that enables the light to be where we need it, when we need it, etc., that we will get the best result. So if we put these together, we will get the solution that will give us what we want out of lighting at night. But we have to bring both of those elements to the table when we discuss lighting designs. So we're trying to keep people aware of the problem, tell them what the benefits are of the different technologies that are available, and help the lighting designers connect those two things in order to create better designs that are better for the night sky. So I always show this slide when I ask, how do we solve this problem? And when I give talks in the United States, a lot of people don't know where this is in the world. This is an image taken by an astronaut out the window of the International Space Station. And it is in Asia. And I think probably most of you can guess that this is mainland China. This is the Korean Peninsula. So here is South Korea, and here is North Korea. That bright line right there is the demilitarized zone between the two countries. This is not how we should solve the problem. The least of which because these people suffer because of what their government will not allow them to have. And electricity and lighting is one of those things. Turning the world's lights off is not the best approach to solving the problem of light pollution. Right? I would argue that maybe we don't want to go to the opposite extreme for a city like Seoul. That may be a little too much light. But this is not the way to do it. So instead, how do we realistically solve the problem? And that turns out to be relatively simple. And again, it goes back to this notion of awareness and attention to the issue. We think that if people re-examine the relationship that they have with the use of all of this light, they would find that they need less of it in order to achieve the same goals. And so when I talked about mindfulness, or this notion of being consciously aware of the use of light in the previous slide, is what we intend here by this idea, where we say, only put the light where we need it. Make sure it's the right amount for the task, and not too much, but also not too little. Because again, reducing light below safe levels is not a realistic way of solving the problem. We'd also like people ideally to think of the color of the light as well, because again, the Rayleigh scattering that's associated with very blue sources of light has a tendency to increase the problem. And ultimately, use what we call adaptive controls. This is something that the new technology really enables for the first time. We can turn the lights on and off very easily. We can change the intensity of the light throughout the night. So if you think about early in the evening, when a lot of people are still outside, they're on the streets, they're on the sidewalks, they need more light to be able to see. But later on in the night, when the frequency of use of those spaces is less, we can bring the light levels down appropriately. We can use less electricity. We can put less light into the nighttime environment, and we can still maintain public safety. So we have devices such as motion sensing circuits, timers, dimming circuits that can help us achieve these goals. And this is something that's very easily done now. It was not possible with earlier lighting systems, such as the sodium lights I showed you in the lawn. We can do that now with LED. So if we do LED properly, we can get a very good outcome. But again, that takes thinking about how we use this light and making sure that it's correct for the situation. So if we go in that direction, we change the way we do lighting design, we change the kind of light that we put into the environment, how do we know if the change worked? There's a few ways of getting at this information. One way, as I've suggested before, is that we can use these Earth-orbiting satellites to measure the light that's coming up from below. So here's one of those satellites. It's called Suomi, that was launched by our National Oceanic and Atmospheric Administration in the United States. And here's one of its images. It's looking across the central provinces of Canada. And you'll notice here that not only do you get the lights from the cities, some of which are labeled here, but you get this kind of swirling light up along the upper part of the image, which is the aurora borealis. So it's naturally occurring light. The satellite sees all of it. But we have image processing techniques that can remove the contribution from the aurora and from other natural sources. So one way of figuring out if the light from our cities is changing is to simply watch the emission of light into space, and we can do that from Earth orbiting. We can also get more detailed information from the astronaut photos. We now have many thousands of these images that have been taken by the astronauts over the 20-year lifespan of the International Space Station. This project, called Cities at Night, is a citizen science initiative that helps us identify which city appears in the image. So if you look at this image, you might not know where that is, but somebody who lives in London, in the United Kingdom, would recognize the pattern of streets, and there's a ring road around the city, and you can even see the course of the river through the city because it's dark. So by connecting the people who live in these places with a database of images, they can recognize the city and assign a label to it. This is important because the position information that is recorded when the astronaut photographs are taken refers to the point on the Earth immediately below the space station. So if an astronaut is looking at a large angle out one of the windows, the position on the ground may not match the position of the place that they're looking at with their camera. So it's important to manually, with human identification, find the names of the cities. This project has been very successful at that. And the best benefit of it is that the spatial resolution of these images is very high. So, for example, Suomi sees a resolution element that's about 750 meters per pixel, which is good, but it doesn't give us very much local detailed information. The astronaut images, such as this image of London, in some cases has a resolution of less than 50 meters. So much more detailed information if we can match up the cities with the images. And that's what this project intends to do. We can also make measurements from the ground. There's an inexpensive device called a sky quality meter. There's an example shown on the right. It's a battery-operated device that one merely holds up overhead and presses a button, and a few seconds later, a number appears on this display. And the number is calibrated in what we would call an astronomer unit, which is a magnitude per square arc second. So it's a surface brightness unit of the sky. And it operates logarithmically in steps towards higher numbers that mean a darker night sky. So we can get very sensitive readings, but these are single channel readings. And by that I mean that there's a piece of semiconductor inside the device that just sees all of the light within about 20 degrees of the zenith and makes a single measurement that averages together all that light. It doesn't tell us anything about what's happening around the sky. But now at least we have a point of comparison where I can take a measurement in downtown Taipei, I can take a measurement at home where I live in Tucson, I can directly compare those numbers, and that will tell me by how much the brightness of the sky differs at those places. But we would like to know more than that. And to do that, we have to use some kind of multi-channel device, like a camera system. So here's an example of one of these cameras that was developed by the United States National Park Service. And the output from the camera looks like this. And it is color-coded according to the brightness of the sky. So this is an image of the entire sky that is projected onto a flat surface, so that the zenith runs along the top here, the horizon runs from north through east, south, west, and back to north. So this is the entire sky. And now we can tell where the city is, right? The city is in this direction. There's not much light on the horizon over here on the north, but to the south and west, that's where the majority of the light is coming in this case. So this gives us much more detailed information about the sources of light that are affecting a particular place on the planet. And we can follow the evolution of this light in time so that we know if any of the interventions that we undertake are useful. Do they produce the desired result is what we're after. And lastly, another way that we can do this is by simply estimating the brightness of the night sky using counts of stars made by volunteers. As it turns out, this system, if it's properly applied, is remarkably accurate. And it maps very well to some of these electronic devices that are used to sense sky brightness. But we can put many more people in the field who can make estimates by just counting stars in particular parts of the sky. So there are a couple of websites here where there are citizen science projects dedicated to this that people can participate in. And of course, the more measurements that we can get, the better we're able to characterize the sky brightness in these places. So these are ideas as far as how we can deal with the problem, and then we can come back on the other side of that and ask ourselves whether our approaches to solving the problem actually do work. And we have very positive results so far that are very encouraging. So let's say that we have properly quantified the problem, we've applied some kind of solution, we generate interest among people in the world being a different place, being a place where the sky is a little bit darker at night. How do we make these changes last? How do we make them durable so that in the future we won't see a return to the old behavior in which the sky becomes brighter, brighter, brighter every year? We think the best way to do that is through public policy, and also through lighting best practices. And once lighting designers and property owners adopt these ideas, then they become very standard. And that standardization is important to carry this forward. So there are a couple of kinds of approaches to lighting policy that are, some of them are specific to the country or jurisdiction. A lot of these are very top level and could apply to almost any part of the world. This is just a summary of different approaches that we can take depending upon the level of government. In the United States, a lot of our lighting policy is made at the local level, so individual municipalities, and we have very little influence at our federal level. In other countries, it's exactly the opposite, and the federal government establishes the policies, and the municipalities are bound to follow them. There are aspects that are better or worse to these different approaches. We think that cities do certain things very well in the implementation of policy. We think that national governments do certain things well in that implementation, and that the ideal balance involves some aspects of policy at each one of those levels. But it's not just making laws. We can write laws that govern people's behavior, of course, and govern the behavior of businesses, of organizations, etc. But not all policies are laws. There are other alternatives to this. We can use models, for example. Some of these have more regulatory elements to them and are not so legislative in nature. We have some model policies ourselves, for example. We worked with the Illuminating Engineering Society, which is the world's largest professional society for lighting designers, to come up with some suggested policies that people can implement at different levels. And there are others as well, not just ours, and some of them apply more to situations such as parks and protected areas. Some of them are for big cities, some of them are for small municipalities. The idea is to take the elements that work well in your jurisdiction and then work on implementing those principles. But they're sufficiently applicable in a general way that we can make these model policies work pretty much anywhere in the world. So there are some very specific challenges that are facing us right now, and this is sort of a summary of what these challenges are and how we're approaching trying to solve the problems. I think the biggest thing that faces us is the LED lighting revolution that's making our cities change colors, as suggested. How can we manage this in the way that produces the best result? Because we think that LED can be quite good if it's handled correctly. And so the ideas that are here on the right are kind of embodied by this image. It shows an LED light lighting up this outdoor picnic area. And the light is confined to the space where it's needed. If this area is in use at night, it's an appropriate quantity of light. Presumably the light is turned off after a certain hour when people are no longer present. And you'll also notice that the color of the light is richer in the long wavelengths and doesn't have so much of the short wavelengths. So we would say that's a so-called warm source of light in comparison to cool light. I know that there are regional preferences for light of different colors. In Asia, it is very common to see very, very blue-rich light because it's a cultural preference. We're concerned about this light because we think there are some very distinct harms associated with it. So we encourage people to use light that contains as little of that blue color as possible. And again, the use of the adaptive controls so that the light level can be varied according to the time of night, can be extinguished altogether. We can even talk about, there are certain situations such as road safety where you might need more blue light in the early evening because you want very good rendering of colors. But later in the night when you don't need that, as the traffic volume decreases, you could phase in less of the blue light and more of the longer wavelengths. LED is very good at doing that. But again, we need to make the choice consciously to opt for these sorts of things. An emerging concern now is the use of electronic signs. You're noticing some of these in this part of the world already, where LED enables signs where the message can change throughout the night. These are coming up very rapidly in the US. A lot of jurisdictions do not know how to regulate them, in part because it's uncertain if they are conventional signs like highway billboards, or are they lighting? Well, they have elements of both, and they have to be really regulated with elements of both of those sources. So for one thing, we recommend that the brightness of these signs be controlled. This is something that legislation is very good at. We do it according to surface brightness rather than measuring the light at some distance away from the sign and having to worry about the ambient light in the area affecting that measurement. We prescribe a series of lighting zones, which sometimes, especially in Europe, are called environmental zones instead, that range from 0 for, very natural areas, places like national parks, all the way up to zones 3 and 4, which are heavily developed urban areas, very large cities in the center of the city. And allowing for a certain amount of light, this is a unit that's often called a nit, which is a candela per square meter. And so we're limiting the surface brightness of the sign itself. During the daytime, you might need thousands of this unit in order for the sign message to be seen. At night, that would be far too bright. And the viewer would no longer be able to read the information content of the sign. So we suggest at night that that number drop down to an appropriate level that limits the amount of light emission into the environment, but also allows the sign to do its job, to communicate some piece of information. But this is the kind of thing that needs to be included in law in order to make sure that nobody exceeds these values. We also think that these, and the term I'm using here is what we, in the US we call an electronic message center, so any of these digital signs, really ought to be limited to only certain times of day. And that has to do, of course, with the likelihood that anybody is there to read the message. And in the overnight hours, unless you're in a very large city, there is almost no traffic and no one is reading the message anyway. Those signs really should be turned off to prevent excess light emission. We recommend an 11 p.m. curfew for on-premise signs. That can be adapted to whatever the local law calls for in terms of operating hours. But the idea is to set a time and to say after that time of night and until the morning, as the sky begins to brighten up before sunrise, that the light should be off. A few other things that can be used to regulate these effectively are monitoring the sign on a 24-hour basis in case there are any malfunctions, so that the sign can be extinguished. Having what we call setbacks. What that means is if you have a lighting installation that's near a sensitive area like a wetland or a park, that you deliberately add some distance to the sign between where it is allowed and the boundary of that sensitive area. That's something that you can write into law. Limitations on distraction. For drivers especially, because these signs can change their information content rapidly. So no flashing lights, no blinking lights, anything like that, that would be distracting to drivers. So the message should be slow. It should remain on the screen for several seconds at a time and make very quick transitions from one message to the next. Gradually changing the intensity of the light as you go from a daytime environment to night so that there are no very distracting changes in the sign brightness, and then restrictions on the sizes of the signs. Since surface brightness times surface area gives you the total light emission, which we're trying to reduce. In some parts of the world, lighting for outdoor sports and recreation activities at night is a very important kind of application of lighting. It's also traditionally something that lends itself to some very poor designs for light that are very bad for the night sky. We have some recommendations. This is a summary of what some of these are. In order, instead of having this very bright overlit stadium, you have these lights on these very tall masts that are throwing light beyond the playing surface. You can see in this example, the light is very thoughtfully designed. The light comes up to the edge of the playing surface and stops. So this is very good for the people who live in the residential areas that are near these recreation facilities so that they're not bothered by this light. The light is turned off at a certain hour. It's limited to certain intensity. Again, many of the same principles that I've been talking about all along, but are applied to this, this sort of unique situation. This is something that we're working on right now, is trying to come up with a better way of characterizing the color content of lighting. We're still using the correlated color temperature, which if you have a thermal source of light, like I was showing earlier, something like a halogen or an incandescent light fixture is very good for telling you what the blue content of that light is, but for a non-thermal emitter, such as a light-emitting diode, it doesn't work very well at all. So we would like to come up with some other means of characterizing that light that doesn't involve a color temperature. I have a very specific example of why color temperature is not really sufficient to tell us how much blue light a source is emitting. I often hear in speaking to people in government, after being influenced by sales literature from the lighting industry, that very blue-rich LED installations like 4,000 or 5,000 Kelvin, they say, well, that light is familiar to people because it looks like moonlight. And they say that because if you fit a black body spectrum to the spectrum of the moon, which is this blue curve right here, you get a number that's about 4,000 Kelvin. So the spectrum of the white LED, the solid black line here, also has a color temperature of about 4,000 degrees Kelvin. These sources are not like each other at all. They do not even superficially represent the same kind of light. The white LED is emitting proportionally much more light than the moon is at that wavelength. Whereas on the other end, moonlight is actually more red than white LED lights. So this is a good example of why this means of characterizing the color content of light is not good right now, and we need something to come up to replace this. We're working on that right now. So what I've laid out so far is we have a problem. It's worldwide. We know what is causing it. We know what its effects are. We know that they are harmful. We know that the solution to the problem is simple, and that it depends on people consciously making decisions about lighting. So we could very easily ask, why doesn't it work? And that's where my organization comes in. These are all reasons, right? It's some of the same things as why humanity has been so slow to react to a changing climate, which the science suggests is a result of human activities. We are very complacent as a species. There's a lack of urgency. There's not yet the sense that a catastrophe is unfolding. We might get there, but as with the lighting, we have not yet achieved that. So how can we make things different? Well, that's where my organization comes in. And to tell you a little bit about us and what we do, here are some general pieces of information about us. We have a presence in about 60 countries, 59 chapters in 18 of those countries. We have members all over the world, 3,000 in total. And we were founded 30 years ago. The idea of drawing public attention to the problem of light pollution and suggesting a solution. And again, out of the belief that turning the world's lights off is not a good approach to this problem, we have worked together with the lighting industry since the beginning to encourage the success of markets for sustainable lighting so that the industry would be more likely to produce better quality lighting products. And I think we have been a very good influence in that regard. So this is one of our early logos. It had a very good notion of what we were trying to achieve, that by keeping the light down, we could keep the stars up. That is still our goal after 30 years. This is our mission. Again, note it doesn't talk about turning lights off. It's a positive message. It's how can we preserve this nighttime environment. It talks about the heritage of dark skies. It's something that transcends borders and languages and cultures. It's something that should be non-controversial, that we can all get behind. And how we do it is through promoting of a certain kind of lighting that is responsible in an environmental sense. These are a sample of the things that we do in order to achieve that mission. You'll note that, again, much of it is focused on raising public attention to the issue, raising awareness of it, providing people with the kind of solutions that they can affect in their own communities and create the kind of change that we hope that we will see around the world. And as I mentioned from the beginning, we have worked with the lighting industry to create more effective outdoor lighting products, and we do that through a certification program where if a manufacturer's products meet a set of criteria that we publish on the web, that they can receive a seal of approval that they can put on their packages. So that's very important for consumers to be able to make more informed choices. So 2 slides ago, I said, there's a problem here, right? Because despite this message that I have been giving you, it doesn't appear to be working. The world is getting brighter all the time. So a way of looking at this is to think of something that's called the issue attention cycle. And this comes out of behavioral psychology. And it looks at lots of social movements around the world over history. And there's a fairly standard cycle that these issues go through, where it first requires that a problem is identified, and And then slowly people become aware of the problem. You reach some point of critical mass. People begin demanding change. They want their elected officials to solve the problem. The implementation of the solution takes place. And then gradually you reset to a new level. And maybe there's another problem that you didn't anticipate that becomes more evident after you solve the larger underlying problem. So the numbers that I have put in here are where I think we are at in terms of light pollution worldwide. And again, thinking back to the 1980s when our organization was founded and very few people knew anything about light pollution, it's a very different place now. The world is very different in this regard, and it's a very much more readily identified problem in different parts of the world. And I think we are eventually getting to the point where we will achieve that critical mass and that people will demand those solutions. And that's where we can come in by helping point those out to the people in charge of making the decisions about lighting. So I think there's a very good chance that within another 25 years, 30 years or so, that we could be at this post-problem stage when we have solved the major problem at hand of light pollution, and then moving forward, figuring out how to sustain the change will be important. I do want to point out the place that I live, which I think is a very good example of how things can be done well. It can be done in a way that's responsive to resident needs, providing for the light that they need to safely move about at night, but also keeps a lot of light out of the night sky. The city where I live is called Tucson, Arizona. It's almost 1 million people if you count the outlying suburban areas. And we are host to a number of astronomical observatories. We're one of the national centers for ground-based astronomy in the United States. And about 10 years ago, an effort was made to quantify the value of astronomy to our local economy. And at that time, it was about $250 million US per year. So a very significant contributor to our overall economic activity in the area. This is very important in order to keep that sky dark so we can keep doing the astronomy from the vicinity of Tucson. So that's the motivator for why we have a very comprehensive outdoor lighting policy. So here's a picture of the city as seen from space. There's a certain amount of light here. You can see it follows some of our major highways in the area. Here's a prediction of the brightness of the night sky at the zenith, so the point directly overhead. And there are a lot of people that live in Tucson. The sky is somewhat bright from inside town. But I would argue for a city of its size in America that Tucson is considerably darker at night than most cities. And it has to do with this lighting policy. So here's another way of looking at it. Here's our city as seen from the space station. Again, we have a better resolution than the other kinds of photographs. But you'll see in 2012, kind of like the picture from Italy that I showed earlier, our street lighting system was dominated by high-pressure sodium discharge lamps, producing this very characteristic orange color. You can in fact see how the major streets of our city follow a very regular pattern, and the light delineates that pattern very clearly in that image. So Tucson recently converted over its street lighting from that old sodium system to a new white LED system. And much like Flagstaff, the other example that I showed, there was an intense interest in making sure that the result did not contaminate the night sky with more artificial light. So how do we do that? How do we make this transition so that we can get the energy savings, but also ensure the integrity of the night sky? Again, mindfulness plus technology equals solution. So we're being mindful of the value of the astronomy economy in Arizona, and we're bringing to bear the benefits of LED technology. So to do this, we made some very specific changes. And you can see that we started off with 852 million lumens of light from about 20,000 individual street lights throughout our city. And after the transition, we had reduced the total light emission of the city street lighting system by almost 40%. So we made those lights much less bright during this transition from old to new technology. And I have a specific example of this to show you. This is one of our main city streets in Tucson. This was during the transition. So when I took this image, we had the old sodium lighting system on this side of the street, and these are the new white LED lights. This is the spectrum of that light compared to the spectrum of the light from the sodium system. In between cars, I ran out into the street, put my light meter down. And under the old system, at the brightest part right under the light, I measured 60 lux of light. So it's just a unit for measuring the intensity of light, and it's a linear unit. And then I went and I measured under one of the new LED lights, and I measured 17 lux. So a reduction of almost 75% over the original value, which you'll notice that to the camera, it looks a little brighter here, but it's a comparable brightness, right? This is why we were able to do this without raising opposition from our residents, is that as you go to lower and lower lighting levels, the human eye becomes progressively more sensitive to blue light. So to the eye, these two scenes, so under this light and under this light, look similarly intense. So almost the same brightness. Whereas in reality, we reduced the brightness by almost a factor of 4. So it's very important because not only did we reduce the total energy consumption of the street lighting system, but we also reduced the brightness of the night sky. And we determined this 2 ways. We went and made measurements in the field of the night sky, which is what I'm showing up here. These are images made with a certain kind of lens on a camera that compresses the entire sky into a single image. That's why these are round. And the colors indicate the brightness of the night sky. So this is in a real calibrated luminance unit. And so in this particular case, this is an area that's near our city. The glow is visible on the southwest horizon. This image was taken in 2014 before the lights were converted. And we took another image around the same time in 2017. And you can see that this green right here is less intense in the second image. So there really was less light emitted by our city street lighting system after this conversion. But to convince ourselves that in fact we reduced this, we also looked at those orbital satellite images. So here's our city in 2014. Here it is again in 2017. If I take one of those images and I subtract the other, what's left, you'll notice, is mostly this dark gray. And that indicates an overall reduction of the light emission of the city by about 10%. So why isn't it more like 50%, right? Because we really decreased the amount of light that the street lighting system produced. For one thing, street lighting is only a fraction of the light that the city emits. We have a lot of privately owned lighting as well. And it's regulated by our local lighting policy, but our city grew during this interim between 2014 and 2017. So there was more private lighting than there was before. We know where all the street lights are. We know how much the street lights emit, but we don't have a good count of all of that private lighting. So that's why we got a reduction that was only a fraction of the expectation, because street lighting is a fraction of the lighting in the city. However, we compared this with radiative transfer models and we found very good agreement. So we think that we really did solve this problem at some level as we transitioned to LED while ensuring that we did not yield more sky glow in our night sky and therefore protected it for astronomy. So in the last few minutes, what I want to talk to you about is what we think the future looks like, right? So this kind of brings everything back to the beginning. After explaining what the problem is and what the solution is, where do we go in the future? Well, for one thing, we think that there is a turning point that's approaching, and it has to do with the sales of LED lighting. So with this chart shows is the market share of LED, which has been steadily increasing for the last several years. But you'll notice in the last couple of years here, 2019-20, that the rate of change is beginning to slow. So instead of a gain of 5% or 7% per year, now only maybe 1 or 2% per year. So why is that happening? Well, on the one hand, LED has much longer lifetime in the field than other kinds of lighting. It's very durable. It can last much longer. It doesn't have the rate of failure that other kinds of lighting has. But the other is simply that we're reaching a point of saturation in the market. Much of the world's lighting has already been converted to LED. There is not much left to sell. And some lighting companies are already beginning to exit the market because of a belief that this will turn flat and that there is no potential for growth. In other words, they don't have as much profit to make as they did in the early period when they were still largely creating this conversion with effective marketing. So the days of LED may be mostly over in terms of high sales. The other problem is less expected, and it has to do with that longevity. The lighting companies have been telling people now for a while, if you're a city, for example, and you're considering converting your lighting over from an old technology to LED, then in addition to all of this energy savings, that these new lighting products will be virtually free of maintenance requirements in the field for as long as 30 years. I thought that was interesting because at the same time, these companies typically will only warrant that their products are free of manufacturing defects for about 10 years. And that's because we're beginning to see signs of early failures of the actual products, the electronics that are underneath them. And what I'm showing in this picture is a typical rate of overall failure for any kind of technology. And there's several things that are happening in this. There's an overall failure rate. At any time, any lighting product, for example, at a 5% level might fail in a year for a variety of reasons. But you also have this initial period where there's a high failure rate as the technology is becoming mature. And then later on, at the end of the product lifetime, it starts rising as products become worn out with age. So overall, we expect that there's a high rate of failure initially with a new technology, and then it levels out, and then at the end of the product lifetime, it rises again. Well, if the product lifetime is only actually about 10 years, and there's some evidence to think that, and the first commercial LED products began to be sold in about the year 2010, then the result is we're approaching the end of lifetime for some of these LEDs. And it is much short of the promises of 20 to 30 years that were based on laboratory measurements of the diodes under very controlled conditions. So if the LEDs fail before communities expected them to, this creates a problem for the communities, right? Because they spent a lot of money initially converting their lights over under a belief that those lights would last for a generation. But if they fail at half of that lifetime, many of the same communities will not be able to afford to replace them. We think that is only a few years away. It probably will not be enough to reverse the trend toward more light pollution. But instead of rapidly rising as it is right now, that may begin to turn and eventually reach an equilibrium. So what will happen after the LEDs fail? Well, we're already beginning to think about that. And it's possible that the LED phenomenon will be a relatively short one in the history of lighting, because there are new kinds of lighting technologies under development right now that are considerably more energy efficient than LED and have demonstrated lifetimes that are longer. And they generally have to deal with something called a laser diode. So instead of shining blue LED light onto a phosphor material and creating the other colors, we'll use laser light, so coherent monochromatic light from a diode laser source that then shines off of a phosphor and produces white light. We're also finding ways to make the phosphor materials more efficient so that more of the light that comes from the source reaches the target instead of being converted, for example, into heat and is considered waste energy. So as an example of one of the new phosphor materials, this is a slab of an engineered metamaterial called perovskite. And when grown in the lab under certain conditions, it has exceptional characteristics in terms of converting light over to white from other colors. So we think that it's going to be a blend of these kind of technologies. A laser diode source, an increasingly effective phosphor will yield a result that's much better than what we were currently able to achieve with LED. So that's a glimpse of what we think that the future might look like. So in the end, the question is, what will our future look like? Is this the future skyline of Taipei? Or will it be different? Will it be brighter, or will it be darker? The decisions that your elected officials and members of your community make today will determine the answer to this question in the future. But again, we understand the problem fairly well. We know what the sources are. We know what the solutions are. We know that those solutions are cost effective and that every one of them can contribute positively to solving this problem. Lastly, I wanted to let you know about our new academic institute that's at the University of Utah in the United States. It's called the Consortium for Dark Sky Studies. The subject of dark skies and light pollution as an academic interest is now becoming very rapidly mature. And so we have set up a new center for this study at this American university, and we invite anybody with an interest in doing research in this area to join our effort and become part of our organization. And you're welcome to have a look at our website. And with that, I would like to thank you for your attention, and I am happy to take your questions.
各位大家好，我叫林正秋，今天应该来开场的，很抱歉。不过如果刚刚有翻译的话，大概今天7点大家都走不了。那我拿个东西给各位看。在座大部分都是天文学者跟这个环境的专家。刚刚开场，他其实花了蛮多时间在讲一个东西，这东西就是我手上这个 Melatonin， 其实叫做褪黑色素。这个是我们的这个果中体里面自由分泌的东西。这个东西呢，几万年来在调节我们。我们中文里面有一句话说：“日出而作，日落而息。”而且我们也知道叫做明窗暗室，晚上睡觉的时候要暗。这其实有一些传统的智慧。所以其实虽然 John 他本身是一个天文学，现在也是光学的专家，可他其实 focus 很多有关于这个 medical study。今天有大概第一个主题有大概都有提到这个部分。那后面呢，其实有更多的比较技术性的细节。我看我们当然没有办法一一来翻译了。不过我特别想问一下，在座是不是有一位汪元宏汪博士？汪博士在哪里？汪博士啊，其实你还真应该，大家应该谢谢他节省了非常多时间。哦，他是唯一一个之前看过 PPT 的人，理论上他今天应该跟大家来翻译。不过没关系，反正就是节省时间。我假设大家英文都还不错，他特意讲的非常 plain， 非常平。有没有什么问题要跟 John 来分享？那如果你们要有翻译问题，你讲中文，我帮你们翻译，有没有？我们节省时间。那或者也in English 都 is okay。Yeah, any question for John？ 刚刚有没有介绍那个 Adam？Okay, we have two guests from the IDA. Yeah, another distinguished guest is Adam Dalton. Yeah, this young guy is a major law and urban planning. Is my colleague. Okay, and so she is a very good technician about the lighting. 就是灯光的技术，她很了解。You have please.
Yeah, I have a question. California has the two halves of the road with the old and the new lighting. You mentioned that they look about equally brightness, even though there's less light over here, because more of it is blue. And earlier you had said we should try to avoid the blue light because it scatters further and more. So is this actually an improvement, given that there's now, is there more blue light, or is it the same amount of blue light?
That's a very good question. Just to restate the question, it is after we made this conversion, after I just told you that blue light has problems associated with it, but yet we elected to put new lights in that have a strong blue emission. So if you consider that change, so we've moved some intensity from here over towards the blue, but we made this large reduction in the overall light emission, the total. We're now emitting about 1/2 of the blue light that we were over here, even though it's very small in comparison. Because remember, this is a relative scale, right? So there's not very much blue light, but there was also a lot of light total. So by lowering that, even though we shifted some to the blue, the total blue light emission is less than it was under the old lighting system. Yes, that's a great question.
John, a technical question. Did the lighting have the shutters?
Yes, in both of these cases. It's hard to see in the pictures, but in both of these cases, these are what we call fully shielded. So these lights do not emit any light directly up into the sky. They direct it all to the ground. So even our old system was actually quite good by our standards, but honestly, it used too much light. And so one thing that we want to look at now in the next couple of years is whether there was any impact on traffic accidents or the incidence of property crime, especially property theft. And the hypothesis is that there will be none to the extent that we can detect that in the data. But we have to wait for some time to go by before we get enough data to be able to tell.
Yeah. 大家不用客气，我们把握时间是 Chris。
Hi. So I just wondered, do you have any feeling for what the fraction of light is between different areas? So say personal lighting, civic lighting, business lighting. And then sort of following on from that, do you have a sort of wish list of public policy changes that could affect a specific one of those? Because I think you can see from recent public policy changes on, say, charges on plastic bags that have had a big impact on people's perception that then filter onto other areas, say, that then goes down to other plastic items. Is that something that you can see happening here?
Yes, and I think it's a great example. Depending on the jurisdiction, the move away from single-use plastic bags may not have a real strong effect on the amount of plastic that makes it into the environment. But it's more about retraining the thinking, right? It's getting people to think about how they apply that in other areas. To your first question about the relative fraction of lighting in different kinds of contexts, we think, we can't yet prove, but using those images from space, we think that something like 50% of the lighting in a typical urban setting anywhere in the world is attributable to roadway lighting. So lighting for streets and highways and things like that. The next largest consumer is probably private sector, commercial, then government at different levels. And actually private residential is a fairly small contributor. And it depends on whether you're in a very dense city environment or whether you're in a suburban environment. As far as a wish list, I think the most important thing that we can do is address the roadway lighting situation, obviously, because we think it's such a large contributor. And just shielding that lighting would make a tremendous difference. And so think back to the slide that I showed that had the difference in the city of Flagstaff of moving from one kind of lighting to another. If I aim a light directly up into the night sky, directly overhead, the chances that that light beam makes it through the atmosphere are pretty good. But as I come down towards the horizon, the likelihood of a scattering event back down to the ground increases. So that by the point that I am at a very, very slight upward angle, 1 or 2 degrees above horizontal, has a very high probability at short wavelengths of being Rayleigh scattered back to the ground at a large distance. So the thing we know that makes the most difference in the world is just shielding that lighting so that there's no light emission above the horizontal. It has to all be down. That has the greatest single impact on sky glow, especially at large distances. Second to that is the color issue once again. So it would be for me shielding, especially for roadway lighting and commercial lighting, and then lowering the color temperature to the greatest extent we can.
Thank you.